Today we're taking a look at chapter 14. We're going to start at 14.1, and we're talking about graph theory. So graph theory has lots of applications. We will see some of those as we work our way through. But as with a lot of the sections that we work on, the first part of this just looks a little weird, okay? A lot of definitions, a lot of things that you might not have seen before, a lot of writing. All right, you guys ready? Okay. So the first thing we're going to define is what we mean by a graph. So throw everything out the window about things you've worked with graphs before. This is a definition that's specifically for graph theory. This is simply a collection of vertices, has to have at least one, and edges. Each edge goes from one vertex to another vertex. So you want to imagine something that looks like this. You got a collection of dots, and maybe this graph connects with this edge and this edge and this edge, okay? So if you don't see a dot, then it's not a vertex. Okay, so it's not like points in a plane. There's not like infinitely many points along each of these things that are called edges, and these are not segments, although they look like the segments that you would have done in a geometry course. So edges are these straight segments that we've got sort of drawn in here, and then the points are vertices. A simple graph is a graph in which no more than one edge between no more than one edge between vertices, and no edge from a vertex to itself, or vertex to itself. Now, that's actually what I drew the first time. So let me draw things that you can't have, okay? So this is what is especially like sort of ruling out. So we can't have the first thing says that if we had 2 points, right, 2 vertices, they can't have two edges between them. So you can't have an edge that's right here and another edge that's right here. Okay? So if you can imagine those 2 points or those vertices as buildings on campus, and the segments, the edges, right, as sidewalks, you have to take one sidewalk to get from here, right, we're in Bailey, over to Thurmond. There aren't 2 options. That's essentially what it's saying. The other thing that it's saying is something that would seem sort of weird if it happened, but it does happen, right, is that you can't have sort of these circular, we'll call them sidewalks. I think it's a pretty good picture for our mind. So if you think about like the central oval, how you can just go around the whole thing, right? You don't have anything that going on. We can't do that. So these are the things that we can't have according to this description. And if we do, then it's still a graph. It's just not a simple graph, because the simple graphs don't have these. And in this chapter, the way we're going to be using it, anytime we see the word graph, it's going to mean simple graph. So anytime we have graph, it's going to automatically mean these 2 things can't be a part of our image. Okay, you ready to look at an example? Not yet. Okay, we're still writing. That's okay. So from an algebra standpoint, we're used to looking at graphs that are kind of either smooth, right? Like they've got some sort of fluidness to it. Think of like graphs of like sine or graphs of like a parabola, right? You're used to looking at things that have smooth graphs, or simply a line itself, one straight line, left to right, going indefinitely in both directions, okay? These graphs aren't going to look like this. They're going to look kind of clunky, okay? So here's our first graph that we have. And we see a bunch of dots and a bunch of segments, right? That's what they look like. Remember that the dots are vertices and the segments are called edges. So the question simply asks us to decide how many vertices we have and how many edges. So you're literally counting, okay? So looking at the picture, how many vertices do you have? 7, yep. And how many edges do you have? 7. And they do not have to match, right? You could have more vertices or more edges. That's a possibility. Either way, this one just happens to have the same number of each. Okay, is that all right? Okay, these kind of things are called graphs. We're going to have applications for them, I promise. Just hold tight on that thought. We have something called a degree of a vertex. So the degree of the vertex is simply the number of edges that connect to it. Okay, so however many edges connect to that vertex, that's the vertex's degree. And we're going to go back up. I've got it drawn here on the screen again, but if you've got it in your notes, you can just look back up slightly above and look at the graph that we have from part 1, number 1, and we're going to find the degree of each vertex. So the vertices themselves are listed out in alphabetical, I think it's just A through G, right? So I'm just going to list them out that way as well, just in order, A, B, C, D, E, F, and G. And we're going to write next to it the degree of each vertex. So taking a look at A, what is its degree? 2. There are 2 segments that are going either into or out of, depending on your perspective, A, right? How about B? 2. Okay, C. C is only 1. D, 2. E, 3. F, also 3. And G, 1. Okay, how are we doing? So far, so good. Just a bunch of counting things, right? Okay, cool. All right, now we have a real good math word. This shows up in lots of math courses, upper level kind of math courses. The word is isomorphic. It sounds really like, I don't know, it sounds really difficult. It's a very mathy word. Okay, isomorphic. Isomorphic graphs specifically. So these are 2 graphs such that there is a 1-to-1 matching between the vertices of the 2 graphs and, with the property that if there is an edge between 2 vertices of the one, then there is an edge between 2 vertices of the other. Okay, so the word isomorphic, generally speaking, it kind of means that the objects are the same. There's somehow you've taken one object and you've sort of deformed it, you've changed it, you've stretched it, you've squished it. You imagine Play-Doh, and it's still the same object. You haven't broken it apart. You haven't reconnected it in a different way. You've just sort of mushed it around. That's what it means to be isomorphic. Now, specifically, when it talks about graphs, it's telling you that there's this correspondence. So when it tells you that there's a 1-to-1 correspondence, what that's naturally telling you is you got to have the same number of vertices, right? Each one has to pair up with another one. That's what 1-to-1 means. We've talked about that before. And the same is true for the edges. You can't simply just count the vertices and edges, though. You have to make sure that they match up in the right way. So it's not quite so simple as just counting, like the last problem that we did. But that's not a bad way to start, because if the counting part doesn't match up, it's automatically not going to be isomorphic. Does that make sense? Okay. So we're going to take a look at a couple of examples, or at an example where we're going to compare 2 graphs, and we're trying to decide if they are isomorphic. Okay? I know a couple of you are still writing a few things down, so I'll pause again. Good? Is anybody still writing that I didn't notice? Okay, let's take a look at an example. So these are my 2 images, so just sketch those in there. While you do that, I'm going to read the directions of what we're trying to do for this particular example. So we're going to determine whether the 2 graphs are isomorphic. Okay, it's just the definition from the previous slide. If they are, we're going to label them in such a way, right? Label the corresponding vertices of the two graphs with the same letters, and we're going to color code the corresponding edges. And it is really important to note that sometimes there's more than one right answer when something like this happens, okay? So let me just say real brief that the way that this shows up a lot of times in my math lab is that they do multiple choice things, right? So you're trying to sort of compare from graph to graph. We don't have multiple choice on our screen. It's not super convenient to do it that way from a teaching perspective. So we're going to label them the way that the question is designed, okay? So let's do just a real quick check. Vertices. Do they have the same number of vertices from one graph to the other one? Yes, they do. How about edges? Do they have the same number of edges from one graph to the other one? Do they not? I think they do. Let's count real quick, and I'll remove my count hash marks. So I have 1, 2, 3. This one's 4 and this one's 5. Okay. Yeah. So that's important to realize. If there's no point, right? If you do not see, I'll put it in like it were there. If you do not see a dot right here, then there's no dot. They don't actually cross over. And a picture, there's a couple pictures you can have in your mind, but a pretty good one is like interstates when they go over one another and under one another, right? Y'all have seen that before. There's a place in Moore right now, if you're from the Moore area, where they're building the railroad and the road so that one can go over or under, and I can't remember which direction it is. Norman did it a number of years ago as well. So they want them to go through the same spot, but they don't want the people on the road to have to stop for the railroad. Make sense? So that's sort of the picture you should have in mind, is that there's no depth to these images. They can overlap without actually crossing. Okay, cool. And then the other one doesn't look like it crosses at all, right? And it's got 5 and we're good with that, yeah? Okay, so we're going to take a look then at labeling these the way that they have asked us to label them. It's not a bad idea to start with either something that's the smallest degree or the largest degree. I'm going to suggest the largest degree. So what's the largest degree that any vertex here has? 3. And can you tell me, Polly, which one do you see, we'll look at the first graph, has a vertex of 3? Bottom left. There we go. I'm going to call this one A. Y'all good with that? And I want to label a point in the other graph that also has the same number of degree. So, far left. How about that? Does that work? Okay, so both of those are labeled with point A. Lovely. We have another one with a degree 3, though, as well, don't we? Yeah. So we'll label that one B. So down here is labeled B, and this one over here. Okay, is everybody good so far? Okay, now let's just make sure from both graphs, it says in the graph on the left that A should be connected to B. Is A connected to B on the right? Yeah, so that's good. So we're doing well so far. We only have 2 more points to label, and they both have degree 2 in both graphs. So let's just put one in and make sure that it works. If it doesn't, we'll switch it around. So I'm going to call it C, and I'm going to do the top left. So according to this picture, this point C has to actually have edges that connect to A and B. So if I put C up here, it will do that. Interestingly enough, I have a choice, and I could put C down here and it would do that too, right? This is that disclaimer in the parentheses. There's more than one way to do this, okay? So I'm going to put it at the top. I had labeled it there first. Some of you had already written it. C at the top. The last point, D, goes over here and at the bottom. And just like in the left graph, D is connected to A and B, but not to C. D is connected to A and B in the second graph and not to C. So this is sort of half of the directions. The other half of the directions say that we are going to color the segments themselves or the edges themselves. So I'm going to use different colors. We'll use orange first. And I mentioned segment AB first, so I'm going to color segment AB like this. Okay? If you have, yes?
What part of it does it say that C has to be connected to A and B, but C and D can't be connected?
Yeah, it's over here where it talked about in order for them to be isomorphic, the edges have to match up. If there is an edge between 2 vertices in one, it has to be an edge between 2 vertices in the other. Okay, that's the definition of isomorphic. And here we're trying to decide if it's isomorphic, so we're looking for a way that would happen. And there is always a possibility that something could creation.
Connected on both would
Yes.
still be isomorphic. as
It
well.
could, correct. Yeah, it would. And we'll see lots of graphs where we have differences like that. Okay, does everybody have AB highlighted in something? Some color. Borrow from a neighbor if people are willing to share some colors. I should have brought colors with me today. I apologize. Those of you who are on digital devices like me, we're in good shape, right? Yeah, lots of colors. Okay, you ready for another color? All right, let's change colors. I'm going to go with green. And which one do you want to connect next? What segment?
C and B.
C and B. Okay, so C and B on this one looks like this, and C and B over here looks like this. All right, any new color? I'm going to do blue. You do whatever color you have. It doesn't matter. What would you like to connect next? A and D. Okay, so A and D is the other one that overlaps, it looks like, over here. And A and D over here is right there. All right, I need another color. I'm going to use yellow, I think. I'll use red next, actually. Which one do you want to connect next? A and C. Here's A and C, and here's A and C. And then lastly, I will use pink. And we're going to connect the DB and the DB. Because we are able to do this, right? Make all these connections, pair them up. It's this one-to-one business that we talked about in the directions or the definition on the previous slide. It means that these are isomorphic. Okay? It is a good idea to check the vertices and edges component first just to make sure. Now let me give you another visual imagery of something you might have seen besides our overlapping highways to kind of describe this. Because I mentioned to you before that isomorphic means that you can somehow manipulate it to turn it into the other object, right? Okay. So have you seen they're always mind puzzles where you're trying to manipulate something to get like nails apart from each other or something like that? Y'all know what I'm talking about? And you keep manipulating them to move them around. RJ?
What a Rubik's Cube?
Kind of like a Rubik's Cube, yes, but I want to think about something that doesn't preserve the shape necessarily. Like a Rubik's Cube, every manipulation is still a square or a cube, right? But some of these objects don't look like that. Like my daughter, I should bring it in. Maybe if I can remember, I'll bring it in on Tuesday. She has this thing that manipulates and it turns into all these different shapes, and it's this block, and it turns back into a cube, but it turns into all sorts of other shapes as well. And every single one of them is isomorphic because the object didn't change. All right, so they're manipulating things. I like the ones that are wires better because I think they fit our graph picture a little bit better, where the manipulation of the wires turns things around and you can move things around that way too. So this is an example of an isomorphic graph. Okay, let's look at another one. Connected versus disconnected. So a connected graph is a graph in which we can move from each vertex of the graph to every other vertex along the edges of the graph. And a disconnected graph means you can't do that. So if you want to think real world examples of things that are connected versus disconnected, if you think about, you have to make a connection of what things are. So let's say that our vertices, each vertex is a city, and our edges is a road. Now, this may not be a perfect example, but it does pretty well for this connected versus disconnected idea. There is a road that will take me from where I am right now to New York City, agreed? Lots of roads, but there's a way to get there on a road, agreed? I cannot do that and get to London. Yeah? There's no road that does that. Now, if you change the context from road, right, for your edges to flight path or something like that, now you might actually be able to do it, correct? So the context, the things that you're letting your edges and your vertices be matter to whether or not something is connected or disconnected. This is one of those concepts that trips people up every time they have quizzes and tests in this unit. I don't think it's a very difficult concept, but I think it's the overlapping pieces sometimes that confuse people. So you want to keep remembering that image we saw before, that if there's not a point there, then there's not a vertex there. Okay? It's really important because I think that's the disconnect, like in your brain disconnect, not disconnected graph, that people have when they look at these kinds of graphs with these kinds of questions. Are we ready for an example? Okay. So this kind of looks connected, but there's two pieces that overlap. Actually, there's three pieces that overlap in two places, and they can actually be separated apart. Can you see that? So I have the ability, I'm going to do this, I'm going to draw this a couple different ways, but I have the ability to sort of, and I don't know if I can do this. I'll just draw it in and then I'll erase it. This piece right now, if you can imagine it being sort of shifted downward on my screen, I can't shift it because of the way my tools work here. I would have the ability to pick this up and move it, and it wouldn't actually affect the other two pieces because there's nothing that connects that piece to the other two. Do you guys see that? But it kind of looks like it's connected because of our prior knowledge of the way graphs sort of work, all right? Another way you can do this is you can start with a vertex, and we're going to start with the leftmost vertex. We'll do it in yellow. And we're going to just draw along this path that it goes along, right? Along the edges. So if I draw along the edges that are there, I can go up, and then I have to go down, and then I have to go left because that's the only place that's left to go. And I have completed that entire piece, right? There's no connection of that to the rest. And I can move on to the next vertex. So the next vertex would be this one right here. And if I follow an edge from here out, I would go left and I would arrive at another edge. But again, I'm stopped. There's nowhere else to go. So you can kind of imagine it being like a bridge, right, over a river or something like that you've got going on there. And then the other one that we can do, and we can start, I'll just start at the bottom over here, just because it's a friendly place to keep moving from. From here, I can go up. I didn't mean green. I'm trying to get to be pink. Try again. So I can go up right here. And then I can go over to the first point that's in the middle there. I can go down, and that's fine. I have to pick up my pencil, right? But I can continue going to the right, and then I can go down, and all the pink connects to other pinks, the greens connect to other greens, and the yellows to the other yellows. So when I have the ability to color it in such a way that the pieces don't connect, right? Because again, there's no vertice here or here, right? They don't exist. This would be a disconnected graph. A disconnected graph. And the other question it says is to determine how many components the graph has. So components means distinct different pieces. And that's actually what we did when we colored it. How many are there? There's 3. So there are 3 components. All right, so let's kind of venture back a little bit into a topic we already looked at, which was degrees. So we talked about how we find a degree of every point. This talks about the sum of the degree of the entire graph. So this is sum of the degrees theorem, and it says that in a graph, the sum of the degrees of the vertices equals twice the number or sum of the edges. And we're going to revisit a picture that we saw earlier so that you can see it work, but you can also see why it works before we do the next example. But feel free to write down these pieces. All right, right, so I'd like you to flip back to, let's just use problem number 1. Problem number 1 works well. We'll say where I did it on problem 2. So it's on your first page if you're taking notes, because you can see the sums of the degrees right there real quick. So if I were to take all those degrees and I were to add them up, 2, 2, 1, 2, 3, 3, 1, how am I going to get? How many am I going to get? There's 14. Okay, there's 14. And how many vertices did we have? 7. How many edges do we have? 7. Okay, so looking back at our definition, let's make sure which one it said so that we're all together. This one says it should be twice the sum of the edges. So ours were 7 and 7, so I want to be careful that we're making sure we're thinking about the right thing. Edges is the important part. We have 7 edges over here, right? So we have 7 edges. And if we were to take 7 times 2, we would also get 14, which matches this 14 down here. Okay, so it worked. The sum that we got for this one example was really twice the number of edges. But why should it work? Well, there's a very good reason of why it should work. Think about what happens, and we'll use this edge AD over here as an example. This edge AD connects to both A and D, right? And it's only ever going to connect to 2 vertices. Right? That's the definition of an edge. An edge connects to 2 vertices. So every edge connects to 2 vertices, which means it's going to get counted twice. Every time. It gets counted when we count it up with A, and it gets counted when we count it with D. And every edge has that property. Make sense? Okay, so this is not really a very earth-shattering theorem or whatever, but it is a true theorem. So let's use this theorem for a different kind of an example now that we've established it. It wants us to use the theorem that relates the sums of the degrees to the number of edges without drawing the graph. Okay, so it was easy enough to see with the graph why that should work and so forth, but now we don't have the graph, we just have the details. We have a graph. The graph has 8 vertices. Okay, 2 of the vertices have degree 1, 3 have degree 2, 1 has degree 3, 1 has degree 5, and 1 has degree 6. How can we find the number of edges? This is what we're asked to find.
Divide the total degrees by 2.
Okay, so take a step back then. The first thing we need to get is the
Is the
total degrees, yeah. Okay, so the first thing we're going to do is we're going to find the sum of the degrees. And they give us a bunch of points. They have 2 of degree 1, so we have 1 and 1. Then we have 3 of degree 2, so that's 2, 2, and 2. Goodness, this is not adding well to me. Here we go. 1 of degree 3, 1 of degree 5, and 1 of degree 6. Let's just make sure that's 8 of them. I think it is. Did we count 8 points there? 8 numbers there? Cool. And what is the sum that we get there? 22? Okay, so the sum is 22. All right, am I going to multiply by 2 or am I going to divide by 2 to find the number of edges? I heard both. It's going to be divide because the sum is twice as many as the edges are. Okay, so up here it tells you the sum is twice as many as the edges. So here's my sum. I'll divide it by 2. And I will have the number of edges. And I did not need a graph to actually make that decision. It's probably worth noting that the sum also needs to be even, right? So it will always divide by 2 evenly. If you've got something that's not, you've probably added something incorrectly. Maybe you left one out or typed something in too many times. So just be careful with your addition pieces, but that would definitely be a red flag. There can be an odd amount of edges, but there can't be an odd sum. And we can't have an odd sum because every edge has to be in there twice. Yeah. Okay. How are we doing? Okay, a little bit more terminology. These are ones that get a little confusing, especially the first 2. We have walk, path, and circuit. A walk is a sequence of vertices, each linked to the next by an edge. A path is a walk that uses no edge more than once. And a circuit is a path that begins and ends at the same vertex. Now, some really good imagery of this does work out to being on our campus, okay? So let's imagine, and we'll label it kind of like we did before. Let's imagine that each vertex is a building on campus, okay? And that the edges are the sidewalks. And we can extend the idea of sidewalk to cross the streets and stuff like that. That's okay for the purposes of what we're discussing. So you guys go through walks all the time, right? You go from one building to another building. Many of you live on campus. You started in whatever building you're living in, and at some point today you arrived in Bailey because that's where we are, right? You did a walk to get here. Now, if you crossed any path or any edge, like any sidewalk, more than one time, then you did a walk, but it wasn't a path because you repeated a portion of sidewalk. If you didn't cross any of those sidewalks more than once, then that was a path. Okay? Does that make sense? So a path could be considered an efficient walk, right? Like, it's like when I want to go run errands. I don't really want to have to go back and forth across Shawnee multiple times. I usually try and think about where my locations are and do them in some kind of a efficient order. I don't want to repeat those pieces. A circuit, though, is when you start and end at the same place. Okay, start and end at the same place. You still don't repeat. You don't go over other pieces again, but you start and end at the same place. So imagine again, if you left your dorm room this morning, you went through all of your classes, you did not cross any of your sidewalks more than once, and then at the end of the day, you went back to your dorm room, then that would be a circuit. Okay? All the way around in whatever fashion you went, but you just didn't cross the path or the sidewalks more than once, then you would have a circuit. All right, let's take a look at an example. So we've got the following graph. It wants us to determine if the sequence of vertices is 1, a walk, 2, a path, or 3, a circuit. And it can be more than one. Right? These are those terrible multiple choice questions that you get. I always saw them in history where they say, is the answer A or B? And then C says A and B. And then D says only A, but not B. You know what I'm talking about like that? Okay, it's like that, right? You can have one of these things. You can have multiple of these things. You can have none of these things. We have lots of choices. There are some things that you can't have. For example, by definition, a path is a walk. Do you see that? So if you write down path, you automatically get to write down walk. And a circuit is a path, and a path is a walk. So what does that tell you about a circuit? It's all three. Okay, so pay attention to how these are sort of intertwined together. Let's take a look. And what we're going to do is we're going to draw along our graph, or at least I am, so feel free to leave yours, pristine and not, but I'm going to draw along mine so that we can see whether it works or not, and then we're going to go from there. So I've got A to B, and then B to E. Okay, we're just going to go through them one at a time. Is it a walk? Yes, it is a walk. I'll just change colors as I go. Okay. Is it a path? Yes, it is a path because we did not cross anything more than once. And the last thing is it a circuit? No, it is not a circuit because we did not start and end at the same place. Okay, are we good so far? All right, let's look at B. And I'll change colors. Let's go with green. We'll go with green this time. All right, we're starting at D. So we go from D to C, C to E, E to B, B to D, D to A to E, and E to C. I've got to draw it that way, otherwise you can't see it on top of itself. Okay. Is it a walk?
Yep.
It is definitely a walk, right? I can go through all those sidewalks. It is a walk. Is it a path?
No,
No. Why not?
because we crossed the E and C twice.
Right. We crossed EC twice. In fact, I had to sort of draw it separately so you could see we did it, right? Yeah. So is it a circuit? No. It does start and end at the same place, right? But it's not a circuit because it's not a path. Okay? Very good. So this is a walk only, and I'll say walk only on here just to make sure we can see that later if we look back. All right. A complete graph. All right, a complete graph. A complete graph is a graph in which there is exactly one edge going from each vertex to each other vertex. So imagery on campus, this would be the idea that there's a sidewalk that goes between every single pair of buildings, right? Not one that crosses through another building, right? But one that actually goes specifically between every pair of buildings. That's what that would look like. We don't have that, and we probably don't need that. That sounds like a lot of, pavement to put down, right? It's not necessary. But that's what the image would look like. All right, so we're going to look at this picture, and we're going to determine whether the graph is a complete graph. And if it's not, we're going to explain why it's not. Is this a complete graph? Careful. It almost looks like it is.
We'll say no,
It's going to say no, it is not. RJ, do you have a reason why?
because if it was a complete graph, A would connect to E.
Ooh, all right. So there's actually quite a few things that are missing. A is not connected to E. What else is missing? I'll throw them in there so you can see them. Ooh, C, A is not connected to C. Yeah, E is not connected to C. F to D, F to B, and B to D. There's a lot of them missing, actually, aren't there? There's a lot of missing sort of edges that we get. Now, does that mean that you can't get from A to E? Well, no, of course not. It just means you have to go through another building, right? Another vertex to get there. So all of those pieces are missing. So I'm going to say no because many edges are, and I'm going to use the word missing. They're not missing in the sense that we didn't put them there, but they just don't exist, right? And for example, we'll just list a couple of them that you guys mentioned. There's no A, E, or F, B. There's lots of them missing. Okay, 6 of them specifically. Lots of missing pieces. Okay. We just keep coming back to more and more terminology. Ready for some more of it? Absolutely. Subgraph. So a subgraph is a graph with some of the original vertices and all of the edges that are between them. So like if we had looked at our previous graph where we had 6 vertices, maybe our subgraph only has 4 vertices. But whatever 4 vertices we picked, whatever edges connected them in the first graph, still connect them in the second graph. A coloring is an assignment of a color to a vertex in such a way that vertices joined by an edge have a different color. And a chromatic number is the least amount of colors that are needed to make a coloring. So, once upon a time, the internet didn't exist, right? You couldn't go out there and look at, say, something like maps super easily on your phones. Agreed? And so there's these things called printed maps. Maybe you've seen one. I don't know. Probably in elementary school, they would have drawn like a map, at least like of the United States, and you had all the states and they were in different colors. Y'all know what I'm talking about, right? Okay. So it is a fact that you need no more than 4 colors to be able to color the map of the United States. Okay? And it was proven using this imagery. And what they were looking at is they were looking at states that shared edges not being the same color. So like Oklahoma and Texas can't be the same color because we share a state line. All right? But if we just sort of touch the corner of a state, it could be different. It could be the same color because we don't share an edge. We only share that corner piece. Are you with me? So the reason that might be an important thing to know from the purpose of the past is because color was very expensive to print in. Case in point, yearbooks before about 15 years ago did not have them all in color. So the yearbooks from my high school, we had some color pages. The seniors got the color pages. And there was this portion at the very beginning, and you had to get that in first. I edited the yearbook a couple years in high school and 1 year in college. And so you had to get those colored pages in first because they took longer to print, and the rest of the book was in black and white. Or if you had color, you maybe had like one string of color somewhere along the way, but it wasn't colored pictures. Because every layer of color that's printed has to run through the printing individually. So you run it through once, and then you have to run it through again, and you have to run it through again, and it layers, and it layers, and it layers. And in fact, sometimes even in printed textbooks, you'll see layers of color, and they don't line up right. And so there's happened to be places in different math textbooks that I've used where they wanted a point to lie somewhere, like on a graph or whatever, but it was slightly off when it went back through the printing press the second time, and the dot didn't quite look like it was on that line. Okay? So you wanted to have as few colors that you had to use to print that map because it was cost effective. So this idea of a coloring was really important when printing looked like that. Okay? So how we go about coloring a graph looks something like this. So we're going to choose a vertex. The way we're going to color it, remember it said over here, is that we're going to assign a color to a vertex. So the edges aren't what we're coloring in this context. It's the vertices, the points. Okay, so we're going to assign a color to a point in such a way that the vertices that are joined by edges are different. So we're going to choose a vertex with the greatest degree. So now it really matters. You got to find the one that's got the biggest. And if there's more than one with the biggest, just pick one of them. And you use that color to color as many vertices as you can, provided that they're not adjacent. And adjacent means that they're connected by an edge. And then you pick a different color and a non-colored vertex of the greatest degree. And you repeat the process. And you keep doing this until all of your vertices are colored. And then however many colors it took would be the chromatic number. All right, ready to do a little bit more coloring? And make sure everybody has a chance to write. Okay, so anybody's still writing? You got it? I know it's a lot of writing in this section. It is, I'm sorry about that. Okay, here's our image, and it's very similar to an image we saw before. If you'll compare it back to, I think it's number 7, it's not quite the same graph, but can you see what's different about it? Yeah, there's actually a vertex in the middle of this one. It's just, pay attention. Sometimes there's vertices and sometimes there's not, so this one has one, okay? They're all labeled. So the directions on the previous slide said that we're supposed to choose the vertex that has the highest degree. So, which vertex would that be in this graph? It is G. Okay, so we're going to color G, and I'm going to use yellow. And we are going to color it first. No, it's not going to work. Let's try a little bit bigger. There we go. Okay, so G is on my graph in yellow. And before I just put the yellow pen down, or highlighter down, or whatever you're using, we want to make sure that there's nothing else that can be colored in yellow. Can I color anything else in yellow? Okay, so again, the way I know is I can only color anything else in yellow is if it's not got an edge that connects it to G. So, do any of the other points that are there, A, B, C, D, E, or F, have edges that are not, I didn't say that right. Do they not have an edge connected to G? No. Every other point that's on the graph is connected to G by an edge, right? So I really am done with the yellow color. Does that make sense? So don't just assume you're done. Here we were, but we're not going to be after the next one. Okay, so change colors. I'm going to go with blue. We need the next point of highest degree. Yes, say that louder.
They're all the same.
They're all the same. Do you guys see that? So what does that mean? Just pick one. Just pick one. So we're going to start with A. Sure. All right, so I'm going to color A in blue. Now, there are edges that are not connected to A, right? There's quite a few of them. So can you tell me some edges or some points, some vertices that are not connected to A by an edge? C, D, and E. Does everybody see that? Okay, so I definitely cannot color B or F in blue, but I could color C, D, or E in blue. And I want to pick as many as I can. For example, if I pick D, I can't pick anything else, correct? But if I pick C, then I can also pick E. Does that make sense? All three of those blue dots are not connected by edges to one another. All right, then we're going to change colors. I'm going to go with purple because I haven't done purple today. Well, I've already used blue. How about we just go with boring old pink? All right. All righty then. What letter do you want to go with next? Because we said they're all the same degree at this point. B. All right, so here's B. Now what? You can do D and F. So then, what is our chromatic number? Our chromatic number is 3. It's how many it took us to use in order to make the coloring work. So again, what does this look like in my math lab? It looks like a lot of multiple choice. You're going to see a whole bunch of different graphs. Some of them are going to be chromatic colorings with too many things, right? They're going to have too many colors. There's more than they need. Some of them are going to have things that are connected that shouldn't be able to be connected, right? 2 of them are actually connected by an edge. Are going to both be colored yellow. And you have to decipher which one works and which one doesn't, and then make the statement at the end what the chromatic number is typically how that shows up.
So they always color it in like we don't.
I don't think there's any way that they have in there for you to be able to color it in, which I kind of think is unfortunate, but it would be hard, I think, for the grading end of it, for it to actually be able to grade it in an AI format, because they'd have to make sure that the colors you chose and the points you chose worked, and I think that would be tricky on their end. It's probably coming, but we don't have it yet. Okay, one last thing in this problem. So this is an interesting application for graphs, and we're going to see some other interesting applications. So we've got a party. So at a party, there were 4 males and 5 females, and during the party, each male danced with each female, and no female or male pair danced together. So we're going to draw a graph with vertices representing the people at the party. Okay, so the vertices are the people, and the edges are representing that they danced with one another. Okay, So this is not the same imagery of my sidewalks. I mean, like, it doesn't have a picture that's very intuitive, but the description is still telling us how to do it. All right? And it wants to know how many edges are there in the graph. So a nice way of setting this up is to keep the genders separated. So we put our males on the left, our females on the right, or vice versa. So that's how I'm going to suggest that we do that. It'll make the drawing part of it easier for us later on. So I'm going to put, which one do you want, males on the left or right?
Left.
They should be on the left because there was a sign at a restaurant that we were at in Colorado that says males to the left because women are always right. That's what it said. I should have taken a picture and put it in there. Man, how did I not do that? Okay, so we're going to put our 4 males on the left. Those are our males. And so just as a reminder to us, let me put it over here because it said there was 4 males, right? And then I have 5 females. 1, 2, 3, 4, and 5. And over here is our female pair, or female vertices. Okay, everybody good? Okay, what does it say? It says edges are going to represent danced with, right? That description of danced with. So if I take my first male, just that first dot there, where am I going to draw edges from the first dot? To each of the females on the right. Okay, so it's going to look like this. And in particular, you can see that that male danced with how many females? All of them, 5, right? So it's got a degree, that dot, right? That vertex has got a degree of 5. What about our next male? Same thing. Our graph's going to get real fun. And then,
They forgot to put it to the last one.
oh, I'm sorry. Thank you for catching that. Okay, and then, same thing again. And then we do it one more time. This is the best graph of the day right here. Look at that. So many edges. I probably should have done a little bit thinner so that we could see them more distinguishable, but I think they're okay. Now there's several different ways we can answer the question. We could literally count our edges. That would be fine. And you could do that, especially if they were a little bit less thick, I could count them. I can also look at the degrees, like this is degree 5, right, all the way down. And this is degree 4 all the way down because each of the males danced with 5 females and each of the females danced with 4 males. Yeah, you can multiply, well, not just, okay, so there's 5 over here on the left, right? So each of the 5s, and there's 4 people, right? The 4 men on the left. So there's 5 times 4, or there's 20 different dancing relationship, whatever dances that'd be a lot of dances, but some of them happen simultaneously, so it doesn't work quite like that, right? But there's 20 of them that happened. So the number of edges, whoa, that was not spelled right. Let's try again. Our number of edges is 20 from our picture. This type of graph has a special name. We'll encounter it a little bit later because of the way it sort of separates things apart, but that's for another lesson. Okay, so this one's over.